name is Ivan Lehocki. I'm a geophysicist and space scientist with Lehocki Geospace. I would like to welcome you to my e-lecture titled Improved Rock Property Estimation from Joint Inversion of PP and PS Reflectivities. During my presentation, I will talk about an easy-to-understand approach for inversion of all four elastic ratio parameters entering the well-known Zoeppritz equations. I'll start my presentation with a brief introduction to the Zoeppritz equations. Then I will explain the motivation for this work, specify the goals, introduce the new inversion method, and demonstrate how it works on synthetic examples and a dataset from the Wisting field located in the Barents Sea. Finally, I will close the talk with conclusions. So what do Zoeppritz equations describe? They describe the relations of incident, reflected, and transmitted longitudinal waves and shear waves on both sides of a plane interface. Non-zero incident P wave generates reflected and refracted P and S waves, as the figure on the right reveals. P2P gathers are usually at disposal to seismic interpreters, while the P2S gathers are rarely acquired. This means that the inversion task is underdetermined, unless empirical relations or simplifying assumptions are built into the procedure. However, if P2S data are available, the number of unknowns and the number of equations is the same, making it possible to uniquely invert for all the unknowns. Why is the addition of P2S data important? Because it can provide more information about structure as well as reservoir properties. For example, the comparison of the two highlighted sections reveals that the shear wave data can provide much clearer image of the reservoir interval. It can also detect possible fracturing of the reservoir. Until recently, the P2S data collection has often been considered too expensive and too time-consuming. However, recent development in node technology have made the technology competitive both in exploration and production. Goals of this work are defined as follows: to develop a scheme for joint inversion of P2P and P2S Zoeppritz equations in order to obtain four elastic ratio parameters, namely acoustic impedance ratio, density ratio, as well as VP-VS ratios in layer 1 and 2. To test the method on synthetic examples. Furthermore, to test the joint inversion scheme on a semisynthetic dataset. Now, semisynthetic dataset requires additional explanation. A real P2P data is utilized from which all four elastic ratio parameters are extracted with P2P only inversion scheme, which I do not discuss here. Then, P2S response can easily be calculated by forward modeling. Thus, real P2P and synthetic P2S gathers are used to test the inversion. Point number 4, to compare the results with well-known approximations, such as Gardner-Wiggins, for which only P2P gathers are required. One missing equation comes from Gardner's empirical relations between bulk density and P wave velocity, while the other one is a simple assumption known as the Wiggins approximation. Moreover, the results are compared to results obtained from inversion of linearized Aki-Richards equation seen on the slide. Let me now introduce some terminology used in this work. In their most compressed form, reflection coefficients calculated from Zoeppritz equations depend on 5 parameters. These are acoustic impedance ratio, that is acoustic impedance of layer 2 divided by acoustic impedance of layer 1, which can be easily calculated from intercept of the PP wave, denoted by IPP in equation 2a. Furthermore, density ratio, VP-VS ratio in layer 1 and VP-VS ratio in layer 2. Finally, reflection coefficients also depend on the angle of incidence, theta. Note that in equation 2c, I define an additional parameter, namely a ratio of VP-VS ratios in layer 2 and 1 respectively. The time has come to briefly introduce the joint P2P, P2S inversion method, called Zoeppritz intersection nonlinear inversion, or briefly Zini. Its essence is to reduce the complex Zoeppritz P2P and P2S equations to quadratic or linear algebraic equations, as the figure reveals. Both Zoeppritz equations will give a range of models satisfying the criterion measuring the misfit between the model and the observation. However, in ideal noise-free case, only one point, namely the intersection point, will satisfy both equations. The problem is solved numerically by discretizing the continuous model parameter space as shown below. Note that the scanning parameter space is three-dimensional, since the acoustic impedance ratio is calculated directly from the intercept formula for P2P waves. How exactly are the calculations performed, and what is the criterion for selecting the models that best satisfy each of the two Zoeppritz equations? The philosophy of the calculations is that introduced by Popper in 1959 and fully embraced by excellent geophysicist Albert Tarantola, which states that those models that do not satisfy observations should be falsified, in other words, excluded from the set of possible solutions. One way to select a subset of possible solutions and falsify others is by quantifying a misfit between observed and calculated reflection coefficients with coefficient of determination called R-squared. Setting this number to a value very close to 1 means that we are searching for models that almost perfectly explain the observation, as seen in the left subplot. Relaxing the criterion corresponds to accounting for measurement uncertainties, and a subset of models is sought for which fall between the two dashed lines seen on the right subplot. Let us now calculate reflection coefficients at an interface of shale and cemented sandstone, marked by the red line, from a well in the North Sea. We can see that at small incident angles, the converted shear waves are absent. In order to avoid this problem, Jerez suggests a normalization of P2S reflection coefficients by dividing it with sine theta squared. Additional benefit is the enhanced similarity between P2P and normalized P2S reflection coefficients. In the following slides, P2P and normalized P2S reflection coefficients will be plotted. Taking the same example as in the previous slide, I will show in more detail how the Zinio algorithm works. The goal is to reconstruct the exact layer parameters, that is gamma 1 and gamma 2, entering the calculations of the P2P curve seen in the upper subplot. Note that the x-axis of the lower subplot is the ratio of gamma 2 and gamma 1. Noise level is set to 0, and the R-squared criterion is set to a value very close to 1. This means that we are searching for those gamma 1, gamma 2 density ratio model triplets that follow very closely the datum, which is the blue line in the upper subplot. Out of 110,040 models, only 10 survive the rejection criterion and can be captured by a quadratic fit. Lower subplot also shows that the inversion task is underdetermined when only P2P data are available, because without additional assumptions or equations, gamma 1 and gamma 2 cannot be uniquely solved for. The situation changes when P2S data are at disposal. In this case, a different set of model triplets satisfies the rejection criterion, and the intersection of surviving models from two equations gives the sought solution. A zoomed figure shows that the intersection of the two quadratic curves is very close to, but not exactly on the exact solution, simply due to the discretized nature of the problem. Moreover, we can see that the intersection calculated in gamma 1, gamma 2 space gives slightly different but close to exact results. Finally, the surviving density ratio values give rise to a distribution that peaks almost exactly at the location of the true density ratio. If rounding to 2 decimals, the reconstruction of density ratio parameter is exact. One of the strengths of Zinio method is that it can see far, as demonstrated on the soft shale loose sand interface. The discretization of the problem is the same as in the previous case, shale cemented sandstone interface. A true value of gamma 1 in soft shale, which is set to 4.1, is well above the upper limit of the sampling space of this parameter, which is set to 3.5. Nevertheless, the intersection of two quadratic equations gives a solution close to the true gamma R, gamma 2 values. Thus, even without prior information on the type of rock, degree of consolidation it has been subjected to, and type of fluid saturating the pore space of the reservoir rock, the method will inform us that the scanning space we chose is not the optimal one, and adaptive techniques can be applied to account for that. Using still the same discretization of the model space, when true gamma 1 is lower than the lower limit of the scanning space of this parameter, set to 2, the intersection of the sets of quadratic equations will once again reconstruct close to true gamma 1, gamma 2 pairs, or gamma R, gamma 2 pairs if you wish. It is always instructive to see how the inversion method will perform in the presence of noise. The test is conducted on reflection coefficients generated from interface between shale and cemented sandstones. As seen before, in noise-free case, the true gamma 1, gamma 2 pair is reconstructed by Zinio method. Adding Gaussian noise to true reflection coefficients will distort the selection of models best satisfying the fits to P2P and P2S random points. It is important to emphasize that the fits are calculated with L2 norm. Thus, the intersection of the quadratic lines obtained from the best fitting models will happen away from the true solution. Gamma 1, gamma 2 equals 2.10 and 1.83 in this case, respectively. Changing only the norm of calculations from L2 to L1 pulls the fit to P2S reflection coefficients closer to the true values. This is because the deployment of L1 norm means that the fit is robust, in other words, much less sensitive to the outliers in data points. Therefore, the intersection point in this case is much closer to true gamma 1, gamma 2 pair. The message is that it is always better to employ outlier insensitive norms when making fits to seismic amplitudes. Let us now look at Zinio method on a semisynthetic example. As introduced earlier, real P2P gathers from Wisting oil field in the Barents Sea were used to perform a P2P only inversion of all 4 elastic ratio parameters. Thus, P2S reflection coefficients were calculated by the forward modeling from Zoeppritz equation for P2S wave. The real P2P gathers were assumed to be noise-free, and the Gaussian noise was added to them, as well as to the synthetic P2S gathers, in order to assess the sensitivity of the Zinio method to random noise. Moreover, the results were compared to the inversion results obtained by two other methods, two other and simpler approaches, namely Gardner-Wiggins and Aki-Richards methods, briefly introduced in slide 5. Note that the discretization of the model parameters chosen for inversion of more than 30,000 interface points leads to a coarser 3D parameter space, which reduces the inversion runtime. Moreover, intersection of linear equations rather than quadratic ones gives the optimal gamma 1, gamma 2 pair at each interface point. Finally, R-squared criterion is less strict than in case of inversion of synthetic examples. In noise-free case, all three methods detect the same anomalously high values of gamma 1. However, they overpredict the values in these zones. On Zinio map, only a slight overprediction is revealed, while the maps generated by Aki-Richards and Gardner-Wiggins methods show larger overpredictions. The addition of noise to reflection coefficients barely affects gamma 1 values calculated by Gardner-Wiggins method, while the maps calculated by the other two methods are blurry and reveal salt and pepper noise over the whole interface. Again, starting with noise-free case, the first thing that strikes eyes is that Aki-Richards method gives completely wrong gamma 2 values and that the hydrocarbon zones are barely visible. Gardner-Wiggins method reveals all the anomalies, but overpredicts the values in gas-filled areas, marked by red colors, while the Zinio method gives a very similar image to that of true gamma 2 map. Addition of noise blurs the Zinio image and slightly affects the Gardner-Wiggins map. Finally, the density ratio maps show the advantages of using full Zoeppritz equations in inversions rather than many of the approximations. In the noise-free case, the Zinio method almost perfectly reconstructs the true density ratio map. This time, the Gardner-Wiggins map is useless in terms of absolute numbers, as it overpredicts the values, but it still gives hints of the hydrocarbon-bearing zones. Similar conclusion can be drawn about the Aki-Richards map, the difference compared to Gardner-Wiggins map being that it systematically underpredicts density ratio values. In noisy case, Aki-Richards map becomes very blurry and can only be used qualitatively, while Zinio method still shows a good match to the true density ratio map. It is time to draw conclusions of this work. So the advantages of Zoeppritz intersection nonlinear inversion methods are as follows. Unique and exact inversion of gamma 1, gamma 2 pairs in noise-free case, and decreased uncertainty of inverted values in presence of noise. It can detect interfaces generated by layer properties outside of the expected sample space. Furthermore, it is superior to Aki-Richards and Gardner-Wiggins approaches, and it can also be used when screening P2P and P2S gathers during exploration in areas with limited well control and prior to using more expensive impedance or full waveform inversions. Disadvantage is that it is limited to the assumption used in the derivation of Zoeppritz equations. In other words, plane wave hitting a planar welded interface of two homogeneous, isotropic, semi-infinite elastic layers. This research, as any other, is far from finished and could be branching in many directions. Most importantly, the methodology should be tested on real P2P, P2S dataset. It would also be very interesting to see if this inversion procedure could be extended to take into account real-world phenomena, such as anisotropy. There are two main takeaways of this presentation. Takeaway number one. Joint inversion of P2P, P2S gathers with Zoeppritz equations for obtaining VP-VS ratios in layers 1 and 2 can be reduced to finding solutions or intersections of pairs of quadratic or linear equations. Takeaway number two. Famous geophysicist Albert Tarantola writes that the idea of using observations to infer one best model of the system is wrong. He concludes by saying that data are not to be used to create a model, but instead to falsify models that do not fit the observations. I hope you have learned something interesting from this presentation. If not, let me tell you a joke as a compensation for your time. A man is going to an appointment and he notices that he is lost, so he stops in the middle of the street and asks someone there, "Excuse me, could you help me? I had an appointment at 2 o'clock with a friend and I am 30 minutes late and I have no idea where I am." "Of course I can help you," answers the helpful man. You're in your diesel-powered car around 7 kilometers from the city center, between 40 and 42 latitude north, 58 and 60 longitude west, close to an area affected by a strong magnetic anomaly. You are a geophysicist, aren't you? Asked the guy in the car. Yes, sir, I am. How did you guess that? Very easy, because all of your answers are technically correct, but practically useless. I am still lost, I will be late, and I don't know what to do with your information. You are a politician, aren't you? Asked the man in the street. Of course I am, answers proudly the guy in the car. How did you know that? Because you don't know either where you are, nor where you are heading. You did a promise that you can't accomplish, and you are waiting that other person solves the problem. In fact, you are exactly in the same situation where you were before asking me, but now, for some strange reason, it looks like the fault is entirely mine. Finally, I would like to take this opportunity to thank OMV, with partners, and TGS for permission to publish the AVO data used in this study. A special thanks to Per Avset for valuable inputs and continued support of my work. Lastly, I thank to Tapan Mukherjee and Daniel Hayden for helping me improve this presentation. It was a pleasure showing you this joint P2P, P2S inversion. For this and other e-lectures, please visit and subscribe to EAGE YouTube channel. Thank you.